physics and mechanics of the human body. All right, so we're going to change that title. We're just going to call it Mechanics and Human Movement. And we're going to call it that because we're going to look at a couple of areas of what engineering calls mechanics. Mechanics is divided up into several subspecialties. Statics, which is the study of no motion, an analysis of things that are frozen in place. Dynamics, which is the study of forces in motion. And kinematics, which is the study of the motion itself. In other words, a way to describe motion is what kinematics is about. So when an engineer sits down and figures out how long a crank rod arm on an engine has to be, he's doing kinematics because he's doing calculation of turning rotational energy into linear energy, and he's doing a complex calculus to figure out how long that arm has to be. If you're doing statics, you're looking at something frozen and analyzing the forces at play that have made it static. In other words, made it non-moving. And then dynamics would be the same kind of, the combination of those two things while the system is in motion. We are not going to do that last one today because it's horribly complicated. What we are going to talk about is statics. And we're going to talk about statics because at certain points in some of the lifts we do, there is no motion. And so at that point, we can look at forces, and one of the neat things about statics is you can do, does everybody remember we talked about on Friday night, we talk about moments, right? We talk about moments at various points in the human body, and one of the neat things you can do in statics is because there's no motion, it means the sum of those moments about any joint in that motion is zero. So all of the forces are in balance. And then you can discover some, at least what's to me, some interesting things about human motion. So we're going to start out, I have to give you, I'm going to take about a half an hour maybe, and give you some really basic engineering principles. I'm going to mix some stuff in with that. Now we're not going to do any math, but we are going to do some vector analysis. Everybody remember everybody remembers this analysis, right? Remember the various points, whether we were in tension or compression, and some varying forces. We're going to look at that a little bit. We're going to look starting at prehistoric man. This is a river. And this is our little prehistoric man standing here. He wants to get across the river. He's carrying something. He doesn't want to get wet. So what would he do? He's prehistoric man. Anybody? Well, he's going to cut down our tree here, right? We've got I didn't tell you, we had a big tree here. Sorry about that, but you should have been there already. You guys are starting strength coaches. You should have assumed there was a tree here. He cuts this tree down, right? And we end up with tree across the river. Prehistoric man jumps on the tree, trots across, and if he's like me, he falls in 4 or 5 times, gets back out, goes back to here, and damn it, tries it again until he gets across. And he's built himself a bridge. This was the first iteration of the bridge. And a bridge is nothing but this that's supported on both ends. So it's a beam. And we have to understand some certain things about beams. And the way we draw them in engineering is not like that. We draw them like this. Now there are some variations on that depending on how the beam is supported at each end, but beams have properties. If this is totally uniform and our little guy is standing on here, the material is uniform, the beam has a center of mass, right? Or we call it a centroid when we're talking about materials, but don't worry about that. It just has a line in which everything above that line is above that line, and everything below that line is below, and it's about halfway. We're going to just say that since this is perfect, it is halfway. Well, what's this guy doing to this beam? He's standing on it, so what's he exerting on the beam? The force of his body weight plus whatever he's carrying, that pushes down on the beam, so we're going to replace him with a force. We're going to show it as just an arrow in the direction. What's that going to make the beam do? Bend. It's going to do this, right? It's not going to do the other thing because he's pushing it down. And what happens at a beam is, along this center axis, anything above that center axis in this case is going to be in compression. And the farther away it gets from that central axis, the more compression it's in. And underneath, it will be in tension. We can see this when we did this demonstration, and we pull on the wrench and bend it. In this case, the wrench is going to be doing this because it's bending down the center. Everything up top gets in compression, everything at the bottom gets in tension. Shear is the force that exists in between the planar materials along this axis, that as this section gets shorter, these pieces of material try to get closer together, and these pieces of material try to get farther apart. Shear is the tearing force in between all of those layers that are trying to rip those materials apart. And you can see this. How many of you guys have ever taken a sawhorse and decided you're going to paint your house or do something, so you put a 2x8 across the sawhorses, flat, so that you have a wide thing to stand on, and it bends a lot, right? You guys have done this? What the hell's wrong with you? None of you ever painted a house? Well, what happens if I take two 2x8s and do that? It's stiffer than one, right? And if I take three, it's stiffer than two or one. Now, here's a little thought exercise for you. I'm big on this. I have three 2x8s laying flat on each other. 1, 2, 3. And I weigh them like this. They deflect. Can everybody see how the ends will be staggered out here because they're all the same length, right? So the ends will stagger as this material tries to compress, this material tries to compress, this material tries to compress. They all compress equally because it's the same force on them. So you end up with these boards staggered at each end. Now, we're going to take these boards and we're going to drive nails through them, or we'll glue them together. What happens then? Well, now I've made a beam. I have taken those three individual planks and put them together with a fastener or a glue so that the shearing stress is taken up by those fasteners or by the glue. And this is a really easy way to see shearing force in action. So that when you glue things together, what you're doing is glue performs in tension and compression very poorly, but in shear it's very excellent because it's a thin layer and you're trying to rip it apart. These three pieces are still have the same forces in each of them, but the glue is now restraining them and transferring some of that shearing force to the next member in the construction. They can no longer slide against each other. They're fixed, and now they make a beam. So this is a good visual illustration of the shearing forces that exist in a beam or in a solid beam. The concrete example of this, if you look up over your head and see an I-beam. Where is most of the material in this I-beam? Is in the flanges of the beam. The reason is because the upper surface of the beam is in compression and the lower surface of the beam is in tension, and the web exists to transfer shear between the two. That's what it's there for. If you look under your house, you may have a very similar device made out of plywood and two 2x4s. They groove the two 2x4s, lay the plywood in, glue it all together. You have truss joist. Or you may see some built out of 2x4s with 2x4 webbing in between the two flanges. All devices that do the same thing. Space two different pieces of, or two separate pieces of material apart and transfer shear between them so the upper and lower surfaces can be loaded in compression and tension. Now, we go back to our scenario with the river. What happens if I put enough weight on here? Ends up in the water, right? It deflects and it ends up in the water. So, I'm primitive man, how do I prevent that from happening? What's a way I can prevent that from happening? Sorry?
Put more of them on there.
Well, yeah, you can stack more trees on top of each other, but it'd be really cool if I could get out here in the middle of the river and put a post in here, right? Now, when this thing tries to deflect, I load this post standing in the middle in what? Compression. Why would I want to do that? It's stronger. Yeah. Most materials in engineering and in the human body, bone, are far better in compression than they are in bending. And so when I look at this beam, hey, it would be really, really cool if I could put something under here. It would keep it from compressing. Or it would keep it from deflecting by taking up the deflection as compression. And now I've shortened the span. And so the amount of deflection I get here is less. Let's take that a step further, because we're still using the same materials, but let's say, or maybe not the same materials, let's say I go to stone and concrete. Still have my banks, still have my water, and now because I'm using stone and early cement or mortar, I can build some shapes that aren't. I can build an arch. All right? And this is all, I'm going to say this is all stone here. Everybody's seen the Romans do this with a keystone, right? Here in the center. Now what happens when I push down on that? This is now an arch. Let's say it was really malleable like a bow. It's bowed here, right? And it's just made out of a thin strip of wood. What happens when I push down here?
Transmitting force to the other two arms of the bridge on either side.
How?
Through compression.
Through compression, because these are going to try and get farther apart. So we have to build an abutment here to anchor the ends, to keep them from moving farther apart. And so now I have invented mankind's first means of normalizing force. In other words, taking compressive force in this direction and normalizing it out at an angle, or taking it up at an angle instead of straight down. There is still force being applied by the ground to the bridge like that, but now there's also force being applied by the abutments to the bridge like that to keep it from growing longer or keep it from sagging. And if I want to make this still stronger, I can still put a post in the center. Now we've moved on in age, and mankind is starting to develop wagons and wheels and roads and really heavy shit to carry around and trade. And this has to get stronger and stronger. So what do? I make things thicker, right? And I put in more posts. What's the problem with this? This kind of requires one of those leap to technology things. Well, I'm moving stuff other than with carts, right? One of the first kinds of mankind's early transportation systems was barges. And I've just blocked the river. So when it floods, it's going to knock all this shit apart, and it's going to block my barge traffic. So it'd be really neat if I can figure out how to build bridges without that stuff. And what I'm going to have to do is figure out ways, in order to do so, in order to take force pushing down at any point on the bridge and transmitting it into the ground as a compressive force. Going to have to do that. Sooner or later, the earth has to carry the load you're putting onto the bridge, right? Because, and this is really good, because if you eliminate posts, that's a very important concept, because hopefully this hasn't. We're going to look at a picture. This is the Sunshine Skyway Bridge. You can see that some of it's kind of missing. It's kind of missing because a barge hit the pylons at about 3 o'clock in the morning and knocked one over, and it lost 4 sections of bridge with people on it and stuff, and it was kind of a mess. So getting rid of pylons is a really interesting idea. Pay no attention to this stuff in the back of the picture yet, because that might be the next thing. So we have to figure out ways to go ahead and react out normalized loads a react-out loading in a bridge deck into compressive force, so that there's no need for an abutment at each end of the bridge and a reduced number of pylons in the center of the bridge. This is one version of that. Another version would be a suspension bridge. We'll talk about a suspension bridge in just a second, but this is what's called a cable-stayed bridge. Notice that each of the abutments only take up compressive force. What happens is this. Our man's on the bridge. He's putting a load on the bridge. A cable is attached to various points in the bridge. What do cables carry load in? Tension. They're really good carrying tension. Hence the expression, pushing a rope. You don't push on a rope really good, you pull on it. This cable goes up to an anchorage, and it has a concomitant cable going to another portion of the bridge to help balance the loading, because as engineers we know that there's going to be a certain amount of traffic on this bridge at all times, and loading is going to be fairly evenly distributed. And we have some wiggle room because we have a thick bridge deck that's helping transmit loads between the varying cables and balance this all out. But these cables are pulling in tension on the deck when our man pushes down on it, right? And they're pulling at an angle. They're pulling at this angle. And that angle has both a horizontal and vertical component. The vertical component gets reacted out here because the cable is pulling up with a horizontal component on that particular portion of the bridge deck, and the bridge abutment is pushing up against that cable, and that force is transmitted as compression into the ground. But what about the horizontal force? This is a static situation. Our bridge is not moving, so we know the horizontal force has to be balanced out. What's it balanced out by? Sorry?
The lack of things in the bottom, gravity.
Well, no, it's a horizontal force, so it's normal to gravity. It's reacted out as compression in the bridge deck. You build a beefy bridge deck out of concrete, which is really good in compression, which is why you used it to build your abutments and everything. And now you're using cables to squeeze your bridge deck together. So you have taken a force parallel to gravity on a surface over a river that's suspended, and you have turned all of the forces into compressive forces by use of this cable. Now, a suspension bridge works a little differently. A suspension bridge replaces these cables with cables that hang parallel to the force of gravity. So they're taking up the force directly in tension, and they transmit it to this cable and pull on that cable, which then transmits that force in tension to both ends. The problem is that that force is not normalized in the bridge deck. The compressive force that results from this cable has both a horizontal and vertical component, and that's not being taken up by anything, at least not yet, or there would be movement if it's not taken up. So what do we have to do in a suspension bridge? We have to pin the ends of the cable into an abutment. Has anybody ever looked at Wikipedia and looked at the bridge abutments they originally put in for the I don't know why this is taking so long, but oh, excellent. I violated RIP security settings. That's okay. The heck? I don't know what's happened to my nice picture. There it is. So there's tension in the cable, and it has to be grounded, just like electricity has to be grounded. We put a big mass attached to Mother Earth, and we pull on it in order to provide the tension in the cable necessary to support the bridge deck. I just wanted to explain that because every time I tried this talk out intermediarily with some of the other staff and some of my friends, the first thing they came up with was the suspension bridge. And I really wanted them to come up with this bridge, the cable stay. And you can see that we get rid of all of this elaborate iron structure and bridge deck work and all of these pylons and make a much nice wider gap for our barge traffic to go through so that people don't die when tug pilots fall asleep in the middle of the night, which is what happened here. Wasn't paying attention, rainstorm, didn't see the lights, slammed into the pier, all this collapsed, there were cars on the bridge, it was a big mess. This is what they've replaced it with. Cable stayed. You'll notice that we played around with the cables and the stays a little bit. They're angled, but we can do that with engineering because we can do math. And it's all turned into compressive force both in the bridge deck and the anchorages through the use of tension in the cables. Let's talk about cranes, because we use cranes to pick stuff up. So actually first, let's go over some engineering symbols, because as I'm drawing this, I want you guys to be able to understand some of the symbols I draw. When we as engineers work in learning statics and things like that, we get all these nice little tables and books that tell us how certain things, certain joints or force interactions work. In this case, we're looking at supports and the reaction forces that they are capable of performing. This is one that I want you guys to be familiar with. It's just a roller on a frictionless surface. Now, nothing in the world is frictionless, but some things come relatively close enough that we can use this as a representation. We're not going to worry about this or this because these are other symbols, but we are going to worry about one on the bottom of this chart, which is the same as the first one, but with a rough surface. So with a rough surface, we can provide two reactions, a horizontal and a vertical component. We're going to use the top one far more. So I'm going to draw that over here. We're going to have a flat surface and a roller. We'll save that for later. We'll use that one. And then the other one we're going to use is on the next page. Is the pinned, the smooth pinned joint. Provides two reaction forces, a horizontal and a vertical component. So we're going to set that one aside too. Notice how all of these things react out to ground. That's because the Earth is massive and doesn't move. Again, we're in statics. Things are not moving. And then finally, the fixed or clamp support. This is the one you're all familiar with. You guys have all seen this drawing right here as part of the Friday night lecture. It's just drawn poor substitute for a bolt, but it's just drawn like this. Here's a crappy wrench handle. I'm not an artist, I'm an engineer. This is that. It's the same thing. You have a moment force or a turning force. If the wrench is at various angles, remember there's a horizontal and vertical component to this. Everybody remembers that, right? That's this, a horizontal and a vertical component. We're going to look at that, however, a little bit differently. And I think we'll do that right now, because now's a good time. We'll do it on time. Ooh, we need to move faster. Okay. Wall. Beam coming out from wall. This is the picture we just saw. Weight on the beam. Remember, it's a beam. center line. What's the result of this? It's pushing straight down. So we know over here we have a reactive force pushing straight back up, right? But we also have another force, don't we? We have a turning force. So we need a moment to react here against this force, which is going to want to turn this way, but it's fixed into a wall. So the wall is providing a moment back to the beam, right? Because the beam's not moving. The summation of the forces or moments around this point has to be zero because nothing's moving. So there has to be a twisting force here on this end of the beam in order to prevent the whole thing from moving, okay? Here's an interesting concept. Pin, cable. If I make this cable out of unobtainium and it does not stretch, for all intents and purposes, the moment in the beam goes away. Because now weight along the beam is being supported, the motion at this end of the beam, the potential resultant motion from the force that could happen, is now being constrained by the cable. And it's being taken out as what? Tension. There is tension in the cable. And that tension has a horizontal and a vertical component, right? The vertical component is going to be roughly equal to this. It's not, but we're not doing math, so we're going to say it is. It's roughly equal to this. The resultant horizontal force will be, I think it's cosine of this angle, but it will be a resultant horizontal force that is necessary because your cable is at an angle and your tension has a horizontal component. So now the cable is going to pull back against this point, and the wall is going to provide an anchorage to keep the beam from moving this way. Has everybody got that? There will be some support here depending on the weight of the beam. But this beam's unobtainium, it doesn't have any weight. It's zero weight beam. It has no weight. We're just looking at the force we apply here. What we have done is we have built a cable-stayed structure that takes moment out and converts it into compressive force. This is an important concept. This is an important concept because at the bottom of a squat, when the femur is horizontal to the ground, it is almost totally in compression. You just said, huh? I know a lot of friends have. It is almost totally in compression. So can anybody make a guess, since we're talking about the femur, what we're going to substitute for our cable? Hamstrings, quadriceps, adductors. We're not going to, okay, we're going to look, eventually, we're going to look at it laterally. We're going to look at it in 2 dimensions first. If we get the chance, if I have time, we'll look at it from above and add the 3rd dimension to it. Because there's an important thing that's going on that Feigenbaum and I have been talking about at the bottom, and I don't want to get there quite yet. So this just functions as a kind of a verification. It will probably be in the reading next year, but I found this on the internet from an engineer in Germany. Bone is a compression member in a cable tensioning device, the example of the hip. It's a really good paper. Unfortunately, for you guys, I'm going to have to reduce it because it has, and we're going to look at this example in a minute. This is a tower crane. Let me get rid of all this. This is an engineering diagram of the forces in play in the leg. You can see we have some things labeled here, the sacrum, the pelvis, the femur tibia. So engineers have been thinking about this for a while. The problem is it has a lot of these diagrams in it that mechanical engineers will understand. but everybody else won't. So we're going to go through this and get rid of them. But can anybody see what this structure would be analogous to?
I see a shank and a femur. That's what I see.
Right. Sorry?
Yeah, I even see a sort of. I see a shank.
Yeah.
I see a shank and a.
What we're missing here is if this is the foot and the leg is facing this way, is the knee's not forward of the midfoot, right? This is important, something that we'll get to. And there's no gastroc and no, more importantly, flexor digitalis and flexor hallucis muscle in here. We'll get to those two muscles in just a minute because those are important. Yeah, this is a patella analog up here. But this is another engineering analog of, and engineers have done this historically. If you go back and look at Da Vinci all the way up, what do they try to do? They try to replicate things existing in nature in order to do things. And the tower crane was a way of looking at the hip-knee relationship in order to build a crane. The early designers, you can see how old this is. Look how old these buildings are. They're probably like 1800s. Was an analogous way of building a human knee and supporting weight out here at the hip. This is what they took it from. Another good example. A couple more examples. But you see what they have to do here. This is all, we're all piling counterweights in here, right? We're going to have to look at this a little differently than the crane designers did because we're going to push this point somewhere out over here. And we're going to put the load in a very different place than they do. The load is going to be much closer to the knee. Everybody remembers that, right? Where the load is applied. We're going to draw that and talk about that in just a minute. Last picture. This was a really ambitious one. It's a blow-up of the other one in there. They could get really good reaches for light loads for these things. And it was really handy in early construction to be able to reach really far out over a building and drop stuff in that was relatively light. But you can see some of the same analogs. We're doing engineering here to turn all of these compressive and all of these shear forces into, and all of these normal forces pointing this way because something's going to be hanging here or hanging here, and turning it back into tension. Sorry, it's going to have to be drawn this way. Tension and compression. This is here for balance. This is the midfoot substitution in a crane.
Steve, you might want to tell them what you mean by normal force.
Sorry. Normal force would be any force applied at 90 degrees to a surface. I apologize. When I say normal force, so if I have something, if this is parallel to the ground, 90 degrees to the gravity vector, then a normal force on this beam would be hanging from it in the gravity vector. And we talk about that because we could, for instance, tie a rope and pull on it this way, and then that's going to have a vertical component and a horizontal component to it. And I don't want to deal with these right now. So we're just talking about forces acting parallel to the gravity vector, normal to the surface of the planet.